We go decimal now on Daytime on 2 with more mathematical investigations.
Okay. Hello. Have you ever tried to cut something into 3 equal parts? If I cut here and then here, will these 3 pieces be equal? It's hard to say. So occasionally I cut it like this. First, cake in half, and then those 2 pieces in half again. In other words, I've cut the original cake into quarters. Can you see how that will help me give each of the children 1/3 of the whole cake? Right, equal shares. 1/4 each. And 1/4 left over. Now I'll cut that into quarters. Each of these is now 1/4 of 1/4, or 1/4 times 1/4 if you like. Each of you have one of these pieces. And 1/4 of 1/4 left. Now we cut that into quarters. Well, you get the idea. And before too long, the little piece left over is so small no one worries about it. But in theory, so it looks as if 1/3 is the same as 1/4, plus 1/4 of 1/4, plus 1/4 of 1/4 of 1/4, plus, and so on, forever and ever. Of course, in real life, you can't go on forever and ever. You go on till you've got so near that you can forget about what's left over. But in mathematics, you can invent numbers that go on forever, and they needn't be very large. Suppose I try sharing these 3 rolls between 6 people. First of all, let's try it on the calculator. 3 divided by 6 equals 0.5. Actually, it's much simpler just to cut the rolls in half. 6 pieces. Each piece is half a roll. So 3 divided by 6 is 1/2. But the calculator showed 0.5. That's because it shows fractions as decimals. 0.5 is 5/10, and 5/10 is the same as 1/2. Here it is on a ruler. From here to here is 1 unit. Each small length is 1/10 of that. From here to here is 5/10, 1/2. OK, but suppose I wanted to share the roles between 7 people. Let's start again. 3 divided by 7 equals... That looks very complicated. I'll check it on another calculator. 3 divided by 7 equals an even longer number, but it starts just the same as the other one. Whoever designed these machines had to decide exactly what goes on when you try to divide one number by another. Let's put division under close investigation. Tenths. 30 of them. We can divide most of them by 7. Four tenths each, and 2 over. Put them under the magnifying glass. Hundredths. How many? Three millionths. 3. That looks familiar. We started trying to divide 3 by 7. And we got a 4. Now we've got almost the same problem, dividing 3 of something by 7. Can you see what will happen next? It's quite a decimal. Not surprising we couldn't fit it on a calculator. Heads, I carry on doing this. Tails, I talk to you. Hello. If I were captain of my local cricket club and I'd called tails each time, I'd have lost 5 times in a row. And in cricket, that's very important. In 1985, we went to Nottingham for the start of the 3rd Test against Australia. As soon as the 2 captains had tossed up, we asked the captain of England, David Gower, did he win or lose the toss?
For once won it by using a foreign coin, 10-franc coin.
And what was he going to do?
We're going to bat.
Was that an easy decision to make?
It's one of those jobs where over 5 days you say, well, I think we're better off batting first. And if we bat well, we should do all right.
How important in general was it to win the toss?
The normal thing, the old thing used to be win the toss and bat, because wickets are always good for batting straight early on. Perhaps would turn at the end and make it harder for batting then, so it was always an easy decision.
And what had been his worst run of luck in tossing the coin?
I think I've just had it actually in the last 7 or 8 Test matches. I've probably won the first and the last. This is the start of a new sequence of winning, I hope.
On that occasion, England got a large score, but the match itself ended in a draw. David Gower certainly won't forget losing the toss nearly every time for the 1984 Indian Test series. And you may remember me getting heads 5 times in a row just now. In other words, the more unlikely a particular result, the more likely we are to remember it. We tend to forget the results that happen most of the time. At this school, each pupil is going to toss a coin until it shows heads. On average, how many throws will they take? We asked each person who got heads first time to move to the left. There they are, all in one column. Everyone else tossed again. Those who got heads made a new column. And so on. Let's see what's happening on a diagram. This rectangle represents all the people tossing coins. Suppose there were 256 of them. I think you'd expect that about half would get heads, half would get tails. Suppose exactly half of them get heads on the first toss. That's 128. And of course another 128 don't get heads. We can show this on a graph. Those who get heads in one toss form the first column. The rest have another go. Again, suppose exactly half of these get heads. So 64 people have each taken 2 tosses to get heads. We carry on. Remember, this is theoretical. In reality, it wouldn't be exactly half each time. Only one person who still hasn't tossed heads. They'll need at least 9 tosses. In these theoretical results, it's obvious that the number of tosses which happens most is simply 1. In a real experiment, even if rather less than half the people get heads first time, is the 1 column still likely to be tallest? These are our theoretical results again. There are 32 people who each take just 3 tosses to get heads. So altogether, these people made 96 tosses. That's 32 times 3. If you did a calculation like that for each number of tosses, you could find the total number of tosses. You know how many people did the coin tossing, so you could calculate the average number per person. Here are the results I got. A total of 29 heads and 26 tails, out of 55 throws altogether. As you'd expect, it's about half heads and half tails. But when I'd only done 10 tosses, 8 of them were heads, 80%. A proportion of 0.8. With each toss, the proportion of heads changes. A run of heads makes the proportion of heads go up. But by the time I'd done a lot of tosses, a run of heads didn't make much difference to the proportion. So, if you agree that it's fair to toss a coin to decide how to start a game, you're using one of two different ideas. The first is the long run idea. You say, I tossed this coin hundreds of times, or millions of times. The more I tossed, the more it seemed to show heads about half the time. So we decide that it's likely to show heads about half the throws. We say the probability of heads is 1/2. And of course, the probability of tails is 1/2 as well. But there's more than one way of assigning a probability. You simply look at the coin and say, it looks much the same on each side. There's no reason to suppose it'll come down heads rather than tails. It's an argument from symmetry. Here's a symmetrical solid. 6 faces, each with a different number of dots. I'd say that each face is as likely as any other to land uppermost if I throw it. So, the probability of getting, let's say, 5 is 1/6. In about 1/6 of the throws, I'd expect to get a 5. Most games are for 2 teams, but here's a game for 3 players. You play by moving a marble 1 step at a time, or by jumping over a marble. I've got to get all my red marbles to the opposite corner, and my 2 opponents have got to do the same with their marbles. But how do we decide who will start? Here's one way of deciding. If you toss 2 coins, they can land heads and heads, or tails and tails, or one of each. 3 possibilities. You can call heads, or tails, or both. So, Carl, what are you going to call?
Heads.
Amanda?
Both.
Right. That leaves me with tails. 1 tail. Both. You start, Amanda. Do you think that's a fair way of deciding? Or, if it's not fair, how would you make a fair start for 3 people?